Go, Boby.
Hi, Chinthaka.
So we continue studying the surge coil.
Yeah.
I think the last place we stopped, we talked about the sensitivity of a surge coil and the signal to noise ratio.
Oh, signal to noise ratio, I remember.
Remember we had the thermal noise
Correct.
that contributes to the signal of the surge coil. And based on that,
And then we said that will limit the resolution,
that
the smallest quantity that I can measure.
yes, right, and that depends on
you had discussed a lot of things.
yes.
Maybe a brief.
A brief story, yes. I think that's a good idea.
Yeah.
So we talked about the DC resistance of the coil, okay, and we saw how that directly determines the input noise level, right, and the measurement accuracy. As you said, the resolution, is a key factor that it influences. And so how can you estimate this? I mean, we have an equation for it, but to truly estimate this parameter, you normally need the wire material, right, and the size and so on. Also, another thing we discussed was the equivalent inductance amplitude, right, and that determines not only the frequency characteristics, but also the upper frequency limit of the coil sensor. This is, how can we get this though? Inductance, I mean LCR meter.
If you want to measure,
it,
we could use.
or could you do some modeling or finite element analysis? What would you do if you're designing a sensor and you know what you know?
One thing, your shape is quite standard.
Yes.
So that way it is more or less calculable.
Right.
There is equation for inductance if you have n number of turns with this much of diameter, etc. So it's almost calculable. But if the shape is not very standard, then one could use like you said, some finite element method.
Right. But something that is not so easy to probably estimate is probably the distributed capacitance, right?
Yeah, that's not easy to.
But that also plays a critical role in the frequency characteristics. Because it depends on a lot of things, right? If you talk for the capacitance, here you can see it depends on the diameter of the wire, the dielectric constant of the insulating layer, and the winding method.
Yeah.
Now, when we talk about the winding method, we saw different types of windings have different space factors, for example. Correct. That's just one of the things, correct, that are variable. So, compared to inductance and DCR, capacitance is something. Distributed capacitance is something harder to.
Yeah, it's not so easy to calculate.
Okay, so I mean, based on what we've learned so far, I think this is a nice little summary for students to consider these things when they design a coil, a surge coil sensor. Okay. Now, what do we have here? Now, here is what we call an
It's an electrical equivalent circuit?
Yes. Okay. That's an equivalent circuit model, and we can recognize pretty much all the symbols here, right?
Yeah.
You have your induced voltage, you have your inductance. Let's make this
Coil resistance.
I would say. Capacitance, and then let's say you're measuring the output, the voltage output through let's say some load. This is a match circuit, right? So this is here, matching circuit. Yeah, it's written up here. Okay, so if we were to analyze this circuit, right? This type of circuit can be analyzed by, let's say, like a second order differential equation. So something along the lines of, let's say, t squared plus, and I'm sure this is an equation that the students have probably seen before.
Yeah.
Pretty standard equation.
The difficult one got erased.
Actually, Actually, zeta is a hard one to.
Yeah.
Okay. D0 equals Vi over Lc. Right? Maybe students, some other course have come across this equation.
Yeah.
It's a pretty standard equation. But so we'll talk just about the basic meaning of these symbols. Okay. Now, if you look at zeta, now my zeta is not very good, but it's what we call the damping coefficient, right?
Yeah.
And that is equal to sigma. But sigma and zeta is nearly the same, but they are not. Right? Now, this is your damping attenuation, right? So when we talk about damping attenuation, we mean the degree of decay. Okay? And the nomography here is your resonance frequency of the coil. Yeah. Now, then what is sigma? So I think in this course, especially when it comes to surgicals, the students probably have already come across a lot of equations. But the whole idea is for them to understand what the equations mean rather than for them to derive this equation, because these are standard equations here. If you open a textbook, you'll find these equations. Yes, right? But it's important you understand what the equations mean. So which is why we are kind of trying to expand a bit more on these equations. Here, you have a series component and a parallel component. Okay. So your so this then is calling this your series component, and this is your parallel component. Okay. Then, so we have this now here. Then what is omega? Is 1 over Lc. Okay. Times this brings Rc. Okay, it's Rc here. Yeah. Now, Bobby, I'm sure you recognize this. We already talked about this before. How even if you take out your inductance and capacitance, your output is still reduced due to that current, right? So we talked about that. Right. So then we have zeta here.
Yeah. So in the sigma, half IRL.
IRL. RL, no? RL, yes. Sorry.
RL is the. Sorry, what is it? RC.
Okay. Yeah, we have to stick to one.
Yeah.
I have switched between RL and RC, but
RC may be good.
RC. Yeah. Right. So that's the resistance of the coil. Yeah. Then L plus R0, which is this one here.
Yeah.
Right. See. Okay.